Hello, welcome to my video series of algorithms. This is part 7 of Module 2, Logic and Proof. In this video, we will discuss indirect proof techniques. In the previous video, we have discussed several proof techniques. These techniques attempt to provide direct evidence to show that the proposition is true. For example, in proof by example, proof by exhaustion, and generalization of a generic particular, we all try to identify elements from the domain that can make the proposition true. This type of proof technique is called direct proof or constructive proof. Another type of proof technique does not try to identify the evidence for the proposition, and they are called indirect proof or non-constructive proof. In this video, we will discuss several indirect proof techniques. Specifically, we will discuss proof by contraposition, proof by contradiction, and give an example of other indirect proof techniques that do not belong to the above two classes. First, let's look at proof by contraposition. Proof by contraposition is used to prove a conditional statement P implies Q is true. In some cases, it would be difficult to infer Q directly from P. Proof by contraposition tries to address this issue by proving a logically equivalent statement. Not Q implies not P. The logical equivalence is termed contraposition, and hence the name of this proof technique. Here, instead of inferring Q from P, we will try to infer not P from not Q. And in some cases, the second task could be easier. Note that the second task does not directly infer Q from P. Therefore, it is an indirect proof. As a result, to prove that P implies Q, a proof by contraposition usually contains 3 steps. First, assume that the conclusion Q is false. That is, we'd assume not Q. From there, we show that the condition P is false. In other words, we need to show not P. Then, we can claim that the original statement P implies Q is true based on logical equivalence. For example, prove that for all integers n, if n cubed plus 5 is odd, then n is even. By analyzing the statement that needs to be proven, we see n cubed plus 5 is odd corresponds to the condition P, and n is even corresponds to the conclusion Q. If we want to directly infer Q from P, we need to discuss n from some property we know for n cubed. It means we may need to discuss some properties regarding the cubic root operation, which is difficult. In this case, we can use proof by contraposition, which tries to infer some property regarding n cubed from n. The corresponding computation now becomes computing the cubic of n, which is much easier than computing the cubic root of n cubed. To begin, we assume that Q is false. That is, we assume n is not even, or n is odd. Our goal is to infer that P is false, or n cubed plus 5 is even. Since n is odd, we let n equals to 2k plus 1 for some integer k. Then, we can plug n equals to 2k plus 1 into n cubed plus 5, and get that it equals to 2 times 4k cubed plus 6k squared plus 3k plus 3, which is an even number. In this case, we can conclude that not Q implies not P, and the original statement P implies Q must be true. Therefore, for all integers n, if n cubed plus 5 is odd, then n is even. The second indirect proof technique is proof by contradiction. Its underlying logic can be derived from that for proof by contraposition. Recall that the underlying logic for proof by contraposition is the logical equivalence between P implies Q and not Q implies not P. Now, make P a tautology or T, which means something always true, and make Q the proposition we want to prove. We will then have T implies Q is equivalent to not Q implies C, where C is a contradiction or something that is always false. In this case, if we can prove that not Q implies C is true, we can prove that T implies Q is true based on the logical equivalence. When T implies Q is true, according to the truth table of the implication connective, then Q must be true. In this way, we can prove the original statement Q is true. We can use proof by contradiction when directly proving the proposition Q is difficult. Using proof by contradiction, we can convert the task of proving Q into proving not Q implies C. With the condition not Q, it could be easier to reach a contradiction compared with directly proving Q. Once we have reached a contradiction from not Q, we can claim that the original statement Q is correct. Also, know that proof by contradiction does not directly prove Q. Therefore, it is also an indirect proof technique. Let's look at one example. Prove that square root 2 is irrational. Directly proving the proposition is hard because we have no other conditions to use. Therefore, we will try to use proof by contradiction. We will see if we can derive a contradiction from the opposite of the original proposition. To begin, we assume that square root 2 is rational. Based on the definition of rational numbers, we can express square root 2 as a over b, where a and b are integers with no common factors. Squaring both sides, we get 2 equals a squared over b squared, or a squared equals 2b squared. In this case, a squared is an even number, and therefore a is also an even number. Since a is an even number, a squared must also be divisible by 4. Now, if a squared is divisible by 4, it means that a squared over 4 is an integer. Since a squared equals 2b squared, then 2b squared over 4 is also an integer. It means that b squared is divisible by 2, and it is therefore an even number. When b squared is even, we know that b must also be even. Now, we have shown that both a and b are even. It contradicts the definition of a rational number, where no common factor should exist between a and b. Therefore, our initial assumption of square root 2 being rational must be wrong, and square root 2 must be an irrational number. Given the similarity between proof by contraposition and proof by contradiction, it would help us to understand them better by comparing the differences. The two proof techniques have 4 major differences. First, they are used to prove different types of statements. Proof by contraposition is often used to prove a conditional statement, while proof by contradiction has no such constraint. Second, they are under different logic. Proof by contraposition is derived from the logical equivalence between P implies Q and not Q implies not P, while proof by contradiction is derived from the logical equivalence between T implies Q and not Q implies C. Third, their assumptions are different. Proof by contraposition assumes the conclusion from the conditional statement is false, while proof by contradiction assumes that the entire proposition needs to be proven to be false. Last, their objectives are different. Proof by contraposition tries to show the opposite of the condition, while proof by contradiction tries to reach some contradictions, which may or may not be directly related to the proposition that needs to be proven. While proof by contraposition and proof by contradiction are two important types of indirect proof, some other indirect proofs do not belong to these two categories. Let's look at the following example. Trump is a game played by two players. In this game, a finite number of cookies are laid out on a rectangular grid. The cookie in the top left position is poisoned. The two players take turns making moves. At each move, a player is required to eat the remaining cookie, together with all cookies to the right and below it. The loser is the player who has no choice but to eat the poisoned cookie. Prove that if neither of the players makes mistakes, the player who makes the first move is guaranteed to win. Name the player who makes the first move player 1, and the other one player 2. Since we have a finite number of cookies, and each player must eat at least one cookie in its round, one must eat the last poisoned cookie. Therefore, there's no draw game and a winning strategy must exist. Given a specific configuration of the cookies, that is, which are eaten and which remain, either player can always identify the winning strategy if there is one. Since any instance of the game begins with the configuration that no cookie is eaten, there must exist a winning strategy under this configuration. Know that because player 1 moves first, it will be able to identify the winning strategy from such a configuration and win. To understand the proof better, let's look at what happens to player 2. Because a winning strategy is tied to a specific configuration, after player 1's move, the resulting configuration will not contain any winning strategy if player 1 has made a smart choice. In this case, even if player 2 never makes a mistake, it cannot identify a winning strategy if it does not have one. Know that from the above proof, although we have shown that player 1 will win the game, we have not constructed the winning strategy. In this case, although we didn't use proof by contraposition or proof by contradiction, it remains an indirect proof. In summary, we have discussed indirect or non-constructive proof in this video. We focused on learning proof by contraposition and proof by contradiction. We also showed another indirect proof example that does not belong to either of these two categories. In the next video, we'll discuss mathematical induction. Thank you for watching and see you next time.